Hello everyone. So I'm going to talk about the two pattern drivers that we have in MLIR, specifically the greedy pattern rewriter and the dialect conversion. Some of the things that have changed recently, some of the lessons that I learned over the last years. We also discussed many of those over this course and Discord. And finally, some plans for some of the refactorings that are currently in progress with respect to the dialect conversion. So just to give you a quick overview of the IR traversal mechanisms that we have in MLIR. If I'm missing one, please let me know. The kind of simplest one that you can do is an IR walk, which is a kind of visitor-based API. And basically, we get a callback for every operation or every block or every region, and then you can do something inside of that Lambda function. Then we have the greedy pattern rewrite driver, which is a pattern-based engine, which applies pattern until nothing changes anymore. So basically, until a fixed point is reached. Similar to that, there is the dialect conversion, which is also a pattern-based rewriter. It's slightly different. There's no fixed point iteration. We only look at illegal ops. And we always traverse it from top to bottom. And one thing that I also want to mention, we have the transform dialect, which I think also falls into this graph here, where you can match IR via handles, and then the transform op will determine what should be done with the IR. So in my opinion, if you look here from left to right, the systems increase in complexity and also in terms of runtime overhead, especially the dialect conversion is one that has been shown to be quite expensive. So just to put them, so what I'm going to talk about in this talk is the greedy pattern rewriter and the dialect conversion. So if you put them side by side and compare them, so the greedy pattern rewriter entry point is this apply patterns and fold greedily. You've probably seen it. For dialect conversion, it's apply full or partial conversion. They all come with their respective pattern classes and rewriter classes. The greedy pattern rewriter tries to apply patterns to all ops. It also tries to fold and erase dead ops. The dialect conversion only applies to illegal ops that were marked as illegal according to the conversion targets. It also tries to fold operations, although that's actually unsafe. For the greedy pattern rewriter, there is no guaranteed order of traversal. And there's also no guarantee how often you visit an operation, because if something has changed, the rewriter or the driver may go back and let's say, okay, let's give this another shot. Let's take a look at the op again. Maybe some pattern can match. So you really don't know how expensive this mechanism is. The dialect conversion, it only looks at ops once, and it only looks at illegal ops, and it always looks at that top to bottom. So you have a kind of guarantee, or you have some idea of how expensive this mechanism will be. Finally, the dialect conversion has a rollback mechanism, which can basically undo changes. That's something that the greedy pattern rewriter cannot do. So just a brief overview of what has happened in the last years, what's new. So one thing that we added is listener support. So you can listen to changes that were made by the greedy pattern rewrite driver. This was needed to integrate the greedy pattern rewrite driver into the transform dialect. So there's this new operation, transform.apply patterns, which allows you to run a greedy pattern rewrite from a transform dialect script. There are these expensive pattern checks. There's a new kind of debugging API or extra debugging checks, which helps you find problems with your rewrite patterns. I'm going to show an example for that later. A few additional things for region simplification have been added. Also, the entry points have been kind of unified, so everything takes a greedy rewrite config. And there have been a few of smaller changes that I haven't even listed here. So on the dialect conversion side, we also added listener support, although we don't support it in every case. For example, when an operation was moved, the listener callback will not tell you what the original location of the operation was. That's something that we don't support at the moment. It's also integrated into the transform dialect. The dialect conversion also has these source, argument, and target materializations that you may be familiar with. So these are now optional. I'm going to show an example for that also later. We added support for new API, specifically move up before, move up after. There are still a few things that are not supported. Again, I will show an example later. And there have been many internal bug fixes and additional checks that have been added to basically harden the infrastructure a little bit. So what I want to talk about next is a few of the best practices or like API rules that have also been discussed a lot over this course especially. So maybe the first question is, which one should you use, the greedy pattern rewriter or the dialect conversion? And what I would say is if you don't, in most cases, you can probably get away with just an operation walk, basically this visitor API. This will always be the most efficient solution because there's no work list, no driver overhead. So if you can get away with that, use step one. So you should probably you may want to use a greedy pattern rewrite if you actually need a fixed point iteration. So if you actually need to look at operations multiple times, you need to do something until nothing changes anymore. Or if you want to compose patterns, and maybe this set of patterns is kind of open-ended, some of them coming from this one component, others are coming from this other component. So this rewrite pattern set infrastructure provides a very nice way to combine these things and run it together. For the dialect conversion, it's really useful when you have type changes, meaning you replace an operation with values that have a different type. So the infrastructure will take care of inserting the necessary casts and so on. So that's when you would want to use a dialect conversion. Here's one kind of API rule that I have seen violated a few times in upstream MLIR and also in downstream projects. So I'm talking about the match and rewrite method here. So in a rewrite pattern, you should return success if and only if the IR was modified. So there are a few things that can go wrong if you don't do that. So for example, let's say you return success, but you didn't modify the IR. So then you're telling the rewriter, okay, this pattern matched, it was applied, something has changed. And that tells the driver, okay, let's do another iteration. Let's take a look at the IR again. But actually nothing has changed, so the pattern will match again. And this can trigger an infinite loop. And similarly, if you return failure, but you modify the IR, you tell the rewriter that, well, this pattern did not match, but actually you changed the IR, and now it's in a kind of inconsistent state. So maybe you already started rewriting, and then you aborted. You said return failure. The next pattern comes in, and it sees some 50% applied pattern application here. So that's another problem. For a conversion pattern, we're a bit more lenient. So here the rule is you return success if the pattern was successful, meaning it was either erased or it was converted to an operation modified in place so that it became legal. You're actually allowed to return failure, and the dialect conversion will automatically roll back all changes. So it's a bit more lenient, but for this last point, that's actually something I'm trying to remove to improve the efficiency of the driver. So I'm going to talk about this a little bit later. Here's another kind of best practice for rewrite patterns. The IR should verify after pattern application. This is not a strict MLIR rule, so MLIR only requires you to have valid IR after every pass. But in practice, this is very useful, especially if you have kind of public rewrite patterns, meaning patterns that are exposed via these populate something patterns functions, because here you really don't know which patterns are running together with your pattern. And if you see invalid IR, it's really unclear how do you build a composable system when you don't know what you can expect at the beginning of a pattern application. So this is not always possible. So for example, one case where this is not very useful is if you rewrite functions, function ops and call ops. Typically, you have two separate patterns for that, and in between of those, well, the IR is invalid because the signature has been changed, but the call op has not been changed. So this is not always possible. Another rule, so this is a hard API rule, all IR modifications must go through the rewriter. For example, you should not erase the IR with just op.erase. You have to go through the rewriter. And the reason for that is that the dialect conversion and the greedy pattern rewriter attaches a listener to basically get notified over what has changed. And when you just erase the op, then it may still be on the work list, and the driver tries to schedule or run a pattern for this operation, but actually you're running it on a dangling pointer now, and the driver crashes. So always make sure to go through the rewriter for all kind of IR modifications. So to catch these kind of things, we have a new CMake flag called MLIR's Enable Expensive Pattern API Checks. So what that will look for, it will look for cases where you modified the IR, but return failure, so this kind of stuff. It will also check if the IR verifies after every pattern application. Yeah, and we also make sure that you go through the rewriter, although we don't quite detect all cases, but we detect most of them. So this pattern is, if you use this kind of flag, also make sure to run with the address sanitizer, because if some of these rules are violated, we actually crash, we actually abort the program execution. And sometimes the error messages are sometimes more easier to read, especially if a crash could be caused by the fact that we access a dangling pointer. And if you run with the address sanitizer, you see where this object was deleted. Here's another rule that was kind of longly discussed over discourse. So do not rely on the canonicalizer pass for correctness. And by correctness here, I mean mostly making progress during the lowering. So one problem with these, with the canonicalizer, the canonicalizer is an optimization pass. So it is really, it should be seen as optional. In fact, internally, the canonicalizer pass runs a greedy pattern rewrite, and it has a kind of cutoff. So if we do a lot of work, at some point, we just stop. We just stop, okay, we're done here. We don't want to spend infinite time during, or we don't want to spend too much time during the pass. So we just stop. What that means is that you cannot be sure that the resulting IR is actually in a canonical form. Only half of it may be in a canonical form, or so you really don't know. So what that means is all your pass pipelines, they should also work without the canonicalizer pass. Another issue that you want to keep in mind is the canonicalizer pass runs with all canonicalization patterns. There are a lot of them. So this could be an efficiency problem. Also, other people may be adding new patterns, and now you're seeing changes in your IR. So that's just something to keep in mind. There's also another flag that we added, another CMake flag that we added, MLIR greedy rewrite randomizer seed. So as I said earlier, the greedy pattern rewriter does not give you any guarantee about the order in which ops are being processed. So this CMake flag gives you a way to harden your passes a little bit by manually randomizing them. And then you can see, oh, does it still work? Or do I hit some edge case where, I don't know, my pattern doesn't work anymore because ops are being processed in a different way. So here's an interesting rule for dialect conversion pattern. So there are certain things you're not allowed to do in a dialect conversion, and it's actually not exactly clear what is allowed at the moment and what is unsafe. But one thing that you should not do is, for example, traversing IR. So if you have the problem with the dialect conversion is that some of the changes that it performs are not directly materialized, but they are kind of materialized in a delayed fashion. For example, you delete an operation, it's not actually deleted. We just mark it for erasure, but it's still there. Another example is you replace an op with another op or with other SSA values. We don't actually change the op operands yet. So if you look at the AR, you still see the old IR. And only at the very end, when we are sure that the dialect conversion will succeed, that's when we perform these kind of changes. So if you have code that inspects the IR, you may inspect old IR. So that's why it's generally not safe to look at operations different from the operation that you matched in a conversion pattern. And it doesn't really matter if you look backwards or if you look ahead or if you look forward, you can construct similar examples here. Also beware of unsupported API. For example, do not try to attach a listener or maybe even get a listener from the rewriter in a rewrite pattern or dialect conversion pattern, because the driver will attach its own listener. So if you overwrite that listener, you break the driver. Also, the dialect conversion has some functions that are not supported on the rewriter. For example, replace all uses with. So that will mess with the internal state of the dialect conversion. You can call it, unfortunately, through the via the superclass rewriter base. So if you need this function, probably you can get the replace op or apply signature conversion are good enough for you. But yeah, just keep in mind, replace all uses with is not supported at the moment. So it's something that I'm working on. Here's also an interesting one. Do not try to use a rewrite pattern in a dialect conversion. So if you look at the class structure, everything inherits from pattern, conversion pattern inherits from rewrite pattern. It looks like the API is composable. Every conversion pattern is also a rewrite pattern. But that's not quite true, because a rewrite pattern may use replace all uses with, or it may traverse IR. So all of this is not safe during a dialect conversion. That's why generally you should not mix those two. So unfortunately, we have a few violations of that in upstream MLIR. In these cases, it's actually safe what these patterns are doing because they're not using this kind of API, but keep in mind it's generally unsafe to mix those two. It also goes the other way around, to not use a conversion pattern in a greedy pattern rewrite. That one is a bit simpler, actually. The conversion pattern will actually try to downcast the rewriter to a conversion pattern rewriter, and that will probably fail, and the program will just crash. So either way, you cannot mix those two. You cannot use a rewrite pattern in a dialect conversion, and you cannot use a dialect conversion pattern in a greedy pattern rewrite. There's also a new flag that we add called build materializations equals false. So if you've ever seen one of these error messages, there have been quite a few reports or questions on discourse. Give this flag a try. So what that will do is we disable all materializations, and instead we will insert unrealized conversion casts. And this could be a quite useful debugging tool because the thing will just run through. You take a look at the AR, you take a look at all the unrealized conversion casts, and you can reason about the AR and see why are we missing, why do we have a type mismatch here, what happened. Here just a few quick tips or things that I found useful as I was learning about the dialect conversion. A lot of things are optional. Type converters are optional. With the recent changes, argument source target materialization is optional. Apply signature conversion is optional, so you can do most of this stuff with inline block before and replace uses of our block argument. So if you're trying to learn about the dialect conversion, forget about all these three things. Just look at the dialect conversion in isolation, and then you already took out a lot of complexity. The conversion target is mandatory because that one specifies which ops are illegal, and if you don't have that, then, well, you don't process any ops. Okay, finally, I want to talk about a few future plans that I have for the dialect conversion. One of it is to add one-to-n support to the dialect conversion. So the dialect conversion already has some pre-limited support for that for block arguments. So specifically, the apply signature conversion API supports it, but we do not support it for replace op. So what I want to add is a new function called basically replace op with multiple, where each result is replaced with a value range. And one example where this could be useful, think about a memref, which is one SSA value, and it expands into multiple things which make up the memref descriptor. All of this, by the way, is discussed in this RFC, so feel free to talk to me or comment on the RFC. So what that also means, we need a new entry point to conversion pattern, basically one that takes an adapter that takes an array of, or a list of value ranges. So we need basically a second entry point for this. I have a prototype that does that, and it also works with the op adapter, which is the auto-generated C++ class. So once we have that, we can remove arguments materializations. So we only have source and target materializations then. These are already optional, but now we only have two optional materializations. The argument materialization can be gone. And just as a reminder, the argument materialization was kind of a workaround in the dialect conversion to convert those multiple SSA values back into a single SSA value because we had these limitations in the dialect conversion where not in all places we supported multiple replacement values. And that then finally allows us to delete the one-to-n dialect conversion, which you may be familiar with. It's in this one-to-n type conversion.h, this is a kind of separate dialect conversion infrastructure which lives side by side to the main dialect conversion, so we won't need this anymore. So after that, there's another RFC out on Discourse right now about the one-shot dialect conversion. So the idea here is to provide a faster and more efficient dialect conversion driver that does not have rollbacks. So as I mentioned earlier, in a dialect conversion driver, in a conversion pattern, you can start modifying the AR, and then you can basically say return failure, which means we can't make progress in this pattern, and we roll back all the changes. So this is actually quite expensive because we need to keep track of everything that has happened during the pattern. And maybe you remember Mehdi and Jeff's keynotes during Euro LLVM. And we saw that dialect conversion is actually quite expensive. So I think a pattern application takes around 5,000 nanoseconds per op, while a greedy pattern rewrite only took 160 nanoseconds per op during this particular benchmark. So this is a quite big load on the, this takes a quite heavy toll on the compilation time. Another issue with this current approach to the dialect conversion is that it's quite hard to understand and hard to debug. So for example, if you run with the minus debug flag, you see a mixture of new IR and old IR. Some SSA values are marked as kind of like invalid. So it's quite hard to understand what's going on. So all of this should no longer be a problem. Also, this will allow us to combine rewrite patterns and conversion patterns together. So this should be possible in the new approach. And we can also support methods such as replace all users with, because basically we always materialize all changes immediately. No extra bookkeeping is necessary anymore. Yeah, this brings me to the end of my talk, and I'm happy to answer any questions. Yeah. Yep.
So one thing that we feel like is kind of like missing from the greedy pattern rewriter is something a bit simpler. It's something a bit simpler where we want the work list, we want to apply patterns and add things back to the work list, but we don't want to fold, and we don't want the other complicated things of greedy pattern rewriter. We just want something to initiate, like with an initial work list, and then we want to have a simple way to add things back to the work list and apply the patterns. And so the one thing is, like, can we have an option to not have folding? I know there's an RFC going around.
Personally, I think that's a good idea. We could disable folding or have like a flag in the greedy pattern config object to disable folding. The pattern driver also does some form of CSEing. It's CSEs constants. That's something we could also deactivate. It would be very easy to implement. So feel free to send a PR.
Yeah, and the other thing is, like, we use the notify modified in place to kind of like add things back to the work list. Do you think there should be a more straightforward API to kind of like, explicitly say, just add this all back to the work list?
So I'm not sure if we should expose these kind of internals of the pattern driver. So I would be interested to see why you think that is necessary, and why, in what case do you want to add it back?
So when we know that we changed something, and now all the users, all the users of that, or all the operands now should be added back to the work list, so now they can be processed.
Okay, so we don't do that at the moment.
I know. We do that with notify or modified on all the users and operands.
Yeah. So maybe another way to fix it would be to add an additional condition into the conversion driver. Okay, if the result add all users to the work list. I guess that would be another way to do it.
Exactly, but then all operands, right? Everything that is affected, like, touches this op.
I guess we need some trade-off in between. I see.
What's that?
Forward slice. The forward slice of the
Yeah.
Yeah, that's an interesting idea. I don't have a. Yeah, I guess with this we have to discuss on this course.
More questions?
Thank you.
Yeah.
So like with the, I guess, like, yeah, how you're describing, like, how the conversion pattern, rewrite pattern is kind of lazy with kind of this kind of, kind of work list, not work list, but like items that will be applied, and you don't see a million module. Sometimes when the debugging stuff, like I'll pass dash debug with like, MLIR opt, and that kind of helps me generally, but sometimes I like to, just be like, just dump the module and let me see what it's like, what does it look like currently, and like I can describe.
You want to see everything basically.
That's going to be applied. Like, is there a way to kind of have this almost like a eager mode versus just also like the lazy modes? Like by default have this lazy mode where you go rewriter dots replace op, that's going to lazily apply it, but can we have like an eager mode where everything happens immediately? Would that be easily possible to add, or no?
You mean for the dialect conversion specifically?
Yes. Or yeah.
So yeah, that's what I'm trying to do with the one-shot dialect conversion, to basically apply everything immediately.
I see.
And that's the goal.
I see. Okay. That makes sense. Okay. Thanks.
There is also analysis mode answering that question.
Yeah. Analysis mode is basically you apply a dialect conversion, then you roll everything back. I'm not sure if it's quite what you had in mind, but
I have to give it a shot. I'll take a look.
Yeah. I follow up on the question before that is, do you think it is reasonable to keep extending the configuration of the existing rewriters, or should we rather encourage people to build more rewriter drivers in addition to these ones?
But so what kind of drivers did you have in mind?
I mean, these folks wanted something that analyzes in front. Somebody else was telling me they want a fixed point with a conversion target. So, and one of those, like, how about you try building your own driver, because your needs are pretty specific and it might end up being easier to just build your own reusing the same patterns, which, as you said, it was dangerous, but making sure you can reuse them in a new driver instead of, like, I'm trying to think what's the limit of how big is the configuration of the dialog conversion, for example, should be. It's like
every flag that we adds complexity.
Exactly.
So I think we could provide some building blocks like the work lists, and because both drivers have some kind of mechanism like that, and
So as far as the misuse of APIs goes, is there any effort to fix those at the C++ level, say rename success failure to something more descriptive, change inheritance hierarchy, explicit accessors for things that you would need to modify the stuff that shouldn't be modified?
So for the dialect conversion things that you're not supposed, for example, replace all users with, which you're not supposed to use in a dialect conversion, that will be fixed once we move to the one-shot dialect conversion. Because then the problem there was that we don't adjust the internal state of the dialect conversion. So these issues will be fixed with the return failure, return success. The more I think about this, the way I phrase this, return failure if and only if the IR has changed. So we have, if you go through the rewriter, we always know when the IR has changed. So actually, you wouldn't even need a return value at all. But that would be a pretty big change because all patterns are currently written with a logical result return value.
Yeah. Let's thank the speaker. Unfortunately, that's all the time we have. You can ask your question offline. And let's thank Matthias once again.